Okay. So I'm going to work through this problem that is on mastering for you. You might actually get these numbers. I took these numbers off mastering, so they are randomized. So let's work this out. We got a ceiling fans rotating about a fixed axis with an initial angular velocity, magnitude of 0.26 revolutions per second. It has an angular acceleration of 0.88 revolutions per second squared. Both the angular velocity and the angular acceleration are directed counterclockwise. So the electric ceiling fan blades form a circle of diameter 0.275 meters. Compute the fan's angular velocity magnitude after 1.95 seconds has passed. All right, so let's list all the stuff we know about this part. What is the initial angular velocity? So that's 0.260 revs per second. Technically that's a frequency, but we can use that for angular velocity. What's the final? Well, that's what they want to find. Or we want to find. They want us to find. The position initial, we can always make that. We can make that 0 since they don't tell us where it starts. Position final, no idea. The angular acceleration, 0.88 rev and another 8 revs per second squared. And the change in time, 0.195 seconds. Okay, in kinematics here, if we don't you can use any unit you want as long as the units all cancel out. We got everything in revolutions in seconds. So I'm going to leave it in revolutions in seconds. Do it. Then I'm going to convert to radians afterwards. So I only got to convert once. So I want to find final velocity, and I don't know theta. So you pull out the constant acceleration equations for rotational motion. Not theta is right there. That's that equation, pretty simple equation. Omega final is omega initial plus alpha t. So omega final equals omega initial plus alpha t, alpha delta t. So started out at 0.260 revs per second. We're going to accelerate at 0.0888 revs per second squared, and we're doing that for 0.195 seconds. Boom, plug and chug that out, and what do we get? Right, 0.2260 plus the 0.888 times 0.195. Boom. So 0.43316, but we got 3 digits in here, so 0.433 revs per second. Now what if it wants radians per second? Well, radians per second, we got to do a little conversion, right? We got 2 pi radians in 1 revolution to get rid of our revolutions. So we just multiply that by 2 pi times 2 times pi, and 2.72 is what it would round off to. That's 2.72 rads per second, or seconds to the minus 1. All right, pretty straightforward, that one. Let's do the next one. How many revolutions has the blade turned through? Well, so we want to find this, then we want to find that. So I'm going to use a different equation. All right, through the magic of paper, I'm just going to cover that up. And now we want to find this one and say we don't have omega final. So you look back at your equation sheet. Where's the one with no omega final? Not omega final. That's right there. D1/2 alpha t. So alpha final, rather. Alpha final equal, alpha, that's, what do you call that? Theta. Theta final. Theta initial. Plus omega initial delta t plus 1/2 alpha delta t squared. And everything's the same direction, right? They're all counterclockwise, all positive, so that's good. Started at 0 plus 0.26 times the 0.195. That's in revs. Everything's in revs per second, so we're going to get revolutions when I'm done. Plus 1/2 0.888. 0.195 is the time squared. A lot of you forget to do that squared thing at the end. Plug it into your calculator and find the answer, right? So that's a 6 right there. Right neatly. 0.26 times 0.195. That's the quantity. 0.5 times 0.888 times 0.195 squared. So when I do that, I get 0.041583, and that's revolutions because everything was in revolutions and seconds. So convert that to radians, multiply by 2 pi, right? 2 pi rads for 1 rev. So pop that in there. I got 0.26127 rads, which we got 3 digits, 0.261 radians. Is theta there? All right, pretty straightforward. Another easy one. Now, calculate the tangential acceleration of the point on the tip of the blade at time equal 0.195 seconds. Okay, zoom out a little bit. Well, we got this conversion where acceleration tangential is equal to alpha angular acceleration times r. However, we can only use that. This alpha must be in radians. It's got to be in radians for this. Okay, so I'm going to do that. Well, I know alpha is 0.888 revs per second squared. Well, I can convert that to radians. So 2 pi rads per 1 rev. So I'm going to get, sorry that's jumping around like that. So you get that alpha is 5.57946 rads per second squared, or seconds of minus 2. Multiply that by r, so AT, nope, can't see me, right? You always do this on in class too, right? Work that out, got that number. So AT is alpha r, so that's that number times the radius, which is up here, that's the diameter. So the radius equals the diameter over 2. So 5.579 times 0.75 over 2. And I'm using the whole number out of my calculator. And we get 2.0923 meters per second, right? Because this is in meters. That's meters, and this is seconds to the minus 1. So meters per second we get as our unit. So that's 2.09 meters per second with our significant figures there. So that's how we can find tangential acceleration. Next. Find the centripetal or radial acceleration. Centripetal or radial acceleration. Well, radial or centripetal acceleration is velocity tangential squared over r. So I just figured that out up here, right? What's the tangential velocity at that time? So I need that tangential velocity at that time. That's one way we could do it. We could also do it if it's in radians, right? We know that velocity tangential is equal to omega r if omega is in radians. So this actually could also be omega squared r squared over r, which that reduces to omega squared r. But that's got to be in radians. So that's a new equation for you. You might want to write that down. Anyways, we're going to use this because we have that tangential velocity solved earlier, right? Did we do that one? Well, as you noticed, probably, I skipped right over that one. Right? We did the revolutions. We did the angular velocity, and then I skipped down and did the tangential velocity. And by the way, in that tangential velocity, I think I put the wrong units down there, right? That should be meters per second squared, because this was second squared over there, so it's a second squared there, so a second squared there. Anyways, we got to go back and find out the tangential speed, right? So to do this, we need that. I mean, I could use this and find it because I have the angular speed from my earlier things, but we need to find tangential speed anyways first. So let's go back and do that since I forgot to do that one. Well, that tangential speed is just the angular speed times the radius, but you got to have that angular speed in this. It must be in radians. It could be radians per minute or radians per second, whatever. Usually it's radians per second. So we figured that out, right? We got that that's 2.72 radians per second. I think it's a little bigger number, 2.7216, right? So earlier we found that that omega was 2.72162, and that was rads per second. I found that up here. Well, just plug it in there. So that velocity tangential is going to be all that junk, 2.72. I'm going to put the whole number in my calculator though, times the radius. And as we said before, the radius is half the diameter, so it's half that number. So 0.75 over 2. And this is in radians per second, and this is in meters, so we'll end up with meters per second. When we do that, we get like 1, right? We get 1.0206 meters per second, which 3 significant digits would be just 1.2. So sorry I forgot to do that up there, but there you go. That's how you find that velocity tangential. Now, back here. So doing this one, I'm just going to take that velocity tangential I just found out, 1.0206, square it, and divide it by the radius, which is 0.75 divided by 2, which is what, 0.375? And plug in the whole shebang there, rather than just the rounded. Square it, divided by the 0.375. And we get 2.7 Rotational. Actually, no, it goes 7. There's 4 sevens, and then a 1, and then a 5. And that is meters per second squared, because here we had meters per second. It gets squared and meters. So rounding that off, 2.78 meters per second squared. That's the radial acceleration. Now if we did it with the omega, what if we did it with the omega? So earlier we found omega to be up here we got omega to be the 2.72 rads per second. So what if I do that? 2.72 rads per second, and we're going to square that, and then multiply by that 0.375. And I'm actually going to go up and pull in the whole number, not just the 72. Square that times 0.375, and look what you get. Boink, right? Get that glare out of there. So this was done with the linear velocity, tangential velocity. This was done with the angular velocity. Pretty much the same thing, right? This one they just rounded off the one less digit, and they did there. All right, get the same thing. 2.77. Same thing. Okay, there you go. Little help for that. Hopefully that was beneficial.